This is actually a list of actual applications that we've looked at, and we've worked on each one of them. And the fact that we'll be talking about many different things means that there's a lot of renewal points in the talk. So if you tune out or miss something or take a nap like one of the earlier speakers suggested, you can always catch up. The remarkable thing that we've found is that the circle of ideas around the CTW, both algorithmically and theoretically, and in connection with Bayesian inference, can have very wide-ranging consequences for developing exciting methodological tools in a lot of applications in statistics and time series analysis and in learning. These are some of the ones I'll describe today, and this is the most recent and most interesting one, which is that, in fact, one can even go as far as talking about continuous multivariate general data using this very discrete idea of context tree weighting. So thinking of this as a time series problem, the first thing that I want to mention, and this was realized very early on in statistics in the 50s and 60s and in information theory in the 70s and 80s, is that discrete time series are often harder to deal with than continuous time series. Part of the reason is historical, that a lot of the data and the methods that were used early on were continuous, but part of the reason is also inherently related to the nature of discrete data itself, and it has to do with memory modeling. There's no obvious way to model the memory in your data, even if you, let's say you look at a binary string. Let's say it could be a spike train. We often now have individual neuron recordings. We have the spike train of a single neuron. It's millions of zeros and ones, where you get a 0 when the neuron's not firing and a 1 when you get a spike. Even if you want to model this as a time series with memory of length 20, you need to estimate 2 to the 20 parameters. And this is, of course, outrageous. Although statisticians thought about this starting before information theorists, it was information theorists that came up with a way around this problem, and that was to use variable memory models, and this is sort of the setting on which CTW is built. So a variable memory model, very briefly, says that you can have long memory, but not all of the time. So if I want, let's say I have a time series, this is notation that will remain throughout, time series X on a just finite alphabet of size M. If I have memory length D, I need to know the conditional distribution of the next symbol given any possible D tuple of symbols in the past, and that is not, of course, realistic. These numbers grow very quickly. Instead, what I'll say I'll do is I'll allow myself to look very far back in some cases, but not very far back at all in some others. So this is an example of a variable memory model, and what it says is this is a model for a time series that has an alphabet of size 3. It says that if most recently you've seen a 2, you don't need to look any further back. You know the distribution of the next symbol, and it's given by the conditional distribution, given that you've just seen a 2. But if you've most recently seen a 0, 2, 1, 1, then you need to look 4 steps back, and there's the distribution that you're going to need to predict the next symbol. So models in this setting are given by context trees. The parameters associated with these models are the distributions at the leaves of these trees. So given each context, given the most recent symbols that I've seen, I walk down the tree, I go to the leaf, I find a parameter, theta. Theta is a vector. It's a probability distribution that tells me what the distribution of the next symbol is, given that I've seen most recently a 0, 2, 0, 0, 1. Then I look at this parameter vector, and I read the distribution of the next thing. These are very useful models, not just because they're very economical. They can allow us to have long memory without huge dimensionality. They're also very exciting because seeing a model like this gives you an idea of what the statistical and syntactic structure of the time series is. We very often look at data from a purely agnostic point of view, either because we don't know anything about them, or because we don't want to presume anything about them. If you look at a spike train, or a DNA sequence, or a sequence of syllables in an animal communication song, say a whale song or a bird song, you want to look at it as if you were an alien that just landed on Earth and is reading Shakespeare. You want to pretend you don't know anything about the mechanism that generates the text. You want to figure it out. So determining the underlying structure is not just a question of practical utility. It's also something that's interesting from a deeper scientific point of view. All right, so here's how, this is the basic CTW setting that we'll use in all the applications I'll describe. In order to do Bayesian inference, now we have our models, they're the trees. So we have, let's say we have data, some discrete data from an alphabet of size M. Now we have our models that are context trees up to fixed. We can fix a maximum depth for these context trees. The first thing we want is a prior distribution on models. And we put this distribution, which is a small generalization of the CTW prior. It basically just penalizes bigger models exponentially. You want to avoid overfitting with finite amounts of data. If you don't do anything like this, you'll always choose the biggest, most complex model and be done. But that's not very informative, so you want to avoid that. So we put a prior distribution that makes bigger, more complex models exponentially more complex. And given a model, we want a prior on the parameters, on the distributions, on the leaves of the tree. Remember, we have our model, which is the tree. We have these parameters, these distributions. The prior distribution we put is the most vanilla one. It's a Jeffreys prior. It's a non-informative prior that says that a priori, the distributions at the leaves are independent, and each one of them has a Dirichlet half prior, or you can change these parameters. They don't have to be half if you have some reason to believe they're different. And finally, you observe that if you have your observations, you know the priors, you know the model, you can write down the likelihood. You can write down the probability of the data given the model T and the parameters theta, and you always need an initial segment of length D that I will ignore in most of what I write. I'll just ignore this initial context. And the probability just depends on the parameters. And here you have a product, theta S of J is the probability of seeing J, the conditional probability of seeing J, given that it's following a context S. So you take this probability and you raise it to the power of how many times this has happened in your data. You know, it's like coin flips. Instead of saying probability of 0 times probability of 1, probability of 1 is 0, you can just say it's p to the probability of 1 times, p to the number of 1s times 1 minus p to the number of 0s. It's the same thing we're doing here. And this is the entire setting. The goal of Bayesian inference is then to determine the posterior distributions on models and parameters. And we'll be talking a lot about these. They're very simple formulas. Bayes' rule tells us how to write these posterior distributions down. And most statistics talks, at this point, diverge from where we're going to go. And they say, look, this is very nice and elegant and simple, but you have this denominator here. This is called the prior predictive likelihood in statistics. This is the average of the likelihood of the data over all models and parameters. We can't compute that, and then we'll do blah. Right? This is 99% of modern Bayesian inference. And the difficulty in computing this denominator is the reason why Bayesian statistics was simply a childish, textbook example for about 100 years before MCMC and other methods came along that allowed us to get around this difficulty. So this quantity, this denominator, is the hard part. Computing this is the hard part of doing Bayesian inference, but it's exactly what the CTW computes. So we're very lucky that Frans and his collaborators gave us a way to compute this. And once you can compute this, this is really the key that opens many doors. Right, so a few quick things just to set some notation. This is an average over all models with respect to the prior of the models, and then the average over all parameters with respect to the prior of parameters. This inner integral over parameters can easily be done. This is something that 300 years ago people did in their sleep all the time. This is like a gamma function computation. It's an integral of some polynomial thing. The important thing is that it's a product of what in CTW papers are called estimated probabilities. This is a probability that only depends on counts. AS is a vector that tells us how many times each letter follows context S. Yossi, I can give you the slides. You don't need to take photos. Oh, okay. You should have told me that I could have been a little more. Oh, okay. All right. All right, so the remarkable thing is that Willems and Starkov and Chalkins were able to actually compute this entire average, and the way they did it was using the CTW algorithm. I'll assume that everybody knows what the CTW does. I've written it down here. It just creates a tree consisting of all the contexts that you've seen, and then computes some averages of estimated probabilities starting from the leaves and going to the root. And the nice thing is that in this slightly more general setting, it's easy to show, following a proof that's very much along the lines of the original 1993 preprint of the CTW paper, which was severely butchered before it got published in the Information Theory Transactions. You can actually show that the CTW indeed computes this outrageously complex quantity. And this is, I think, the most realistic and general Bayesian inference setting for which the prior predictive likelihood can be computed exactly. There are Mickey Mouse examples where this can be done analytically, and then there are realistic examples where this is done approximately via sampling or numerical integration or MCMC, but this is the only case where there's a middle-of-the-road approach. You have an algorithm for computing this. We don't have a formula that we can compute exactly. We have an algorithm, but the algorithm is very practical. It works in linear time in the length of the data. It can be implemented sequentially and so on. I really want to get to the applications and show you cool pictures and real data, but please bear with me while I show you a little bit more of the theory of how these applications are going to work. By the way, there was some discussion about common sense and going from theory to applications. In the last presentation, it reminded me of a quote by a Bell Labs researcher in the 50s, in the golden era of the Bell Labs, who said that the difference between theory and practice is very small in theory, but very big in practice. So this is one of the rare cases where we can actually traverse the entire path from very principled development, where it's actually the mathematics that dictates methodology, and this methodology, without fiddling, can be implemented and can be seen to be very successful in cutting-edge hard applications and do as well as the state-of-the-art in some difficult problems. And we'll get there. Now, so we have this big Bayesian key. We can compute this holy grail of Bayesian statistics, the denominator of the posterior distribution, but we can do more. We can also take the CTW, as Frans and his friends did, and instead of computing averages, compute maxima on this tree that you build in the CTW. If you compute maxima at each node of the tree, and you remember the maxima are a constant times the estimated probability of the node plus 1 minus that constant times the product of the probabilities you've already computed at the children of that node. Now, instead of that average, we do a maximum, and we look at who wins. If the parent wins, we prune the tree there. If the children win, we leave them in. So if you do this was the CTM algorithm. This is a slightly more general version that we call the BCT for Bayesian Context Trees algorithm. If you do this, the tree you end up with is actually the mode of the posterior. This is something you really want to know, the distribution on model space. You have all these trees and all these models, you get your data. You want to know the most likely model, and you can get that exactly, again, in linear time using this algorithm. And here's an example of what happens on simulated data. We'll see lots of real data in a moment, but this makes a point. We simulated synthetic data from this model that I showed in the beginning. we got 10,000 samples. It may seem like a lot. It's not a lot, because we're looking at a space of approximately 10 to the 24 models. This is big. It's a lot of models. Even with a maximum depth of d equals 5, it turns out that this framework does identify the true underlying model. And this is cool. This is very classical. This is very much in the spirit of MDL and Rissanen and the papers that were already written by Jalkins and Frans and Starkov and their collaborators 20 years ago. But there's more you can do. Not only can you get the most likely tree, you can get, now remember we have a posterior distribution on trees. So I really want to know if the posterior looks like this or if it looks like this. I want to know if there's a single model that's extremely important and it's very much more likely than all other candidate models, or if there's a big family of different models with maybe different characteristics. So for every fixed k, let's say k equals 5, I can compute by doing more careful bookkeeping. Again, following very much the CTW philosophy, we can compute the k most likely trees with respect to the posterior distribution, but there's a price to pay that the complexity of the algorithm grows with k much more so than it did with all other parameters. Here I've written an exponential. It's not really an exponential. This k to the m can be made smaller, but in practice, it is a complexity barrier. You can't get the 1,000 most likely models. In practice, we rarely can get more than 10 or 20. And you can compute some more things, because again, you know this denominator, you can compute the posterior probability exactly. Not something proportional to it. You can get, for every model you give me, you have your data, you play the role of the statistician, someone brings you data, and you give them a model, and they say, no, we thought it was something else. Maybe the biologist will say, or the economist, or the financier. You can say, okay, well, show me your model, and I'll tell you exactly what its posterior probability is. You can compute posterior probabilities exactly. You can compute posterior odds very, very easily. And for technical reasons, I also noted that you can compute the full conditional density of the parameters, which is the distribution of the parameter vector theta, given a model and given all your observations. We'll be using this in a moment. Here's the same data, the same simulated data, some results in some more detail. So now we took a maximum depth of 10. The real distribution with respect to which the data was generated had depth 5. Here, we're looking at a space of more than 10 to the 5,900. This is infinity. Okay, this is not. This is only a number in science talks. Remember, there's 10 to the 83 number of particles in the universe. So it's a really, really rich space of models. And with just 10,000 observations, we can identify the correct one, and we can see that it has a posterior probability of 36.8%, whereas its prior probability is 10 to the minus 6. So even with 10,000 samples, there's very, very strong evidence for the fact that this is the true underlying structure of the mechanism that produced the data. These two are the second and third most likely models, and these are the posterior odds. This is 6.5 times less likely than the first one, and this model is almost 9 times less likely than the original one. And you can compute the fourth and fifth and sixth and 10th. As I said, at some point you run out of computing power, but even that you can get around. You can actually sample from the posterior. You can because of the fact that the posterior odds are easy to compute, and because of the fact that you know the full conditional density of the parameters, you can create a Markov chain that gives you a sample from or a sequence of samples from the posterior distribution. It's a random walk. It's a Markov chain on trees. So every sample that you get is a tree with parameters, then another tree with another set of parameters, then another tree with another set of parameters. You propose each time either growing a new branch at an existing leaf or pruning a branch that was already there. This way, you're guaranteed that you can create a metropolis within Gibbs chain that gives you samples from both model and parameters in an efficient way. Finally, now we have the first real data set. I wonder if I can play an audio file. No, my memory stick is not here. I'll play this later. Is it Control L? Yeah. This is data from a bird song. And I'll tell you something for nothing. There's a lot of money in this business. People are really interested in creating good statistical models of birdsong because they want to use them for hunting. Of course, our interest is completely different. It's purely scientific, which is to say it has to do with sex. These are all mating calls. Biologists, yeah? Sorry? Oh. Biologists want to understand how mating calls work and, which bird gets more sex than which other bird, and do the birds that have, does the Pavarotti of birds that has the most complex and intricate song get most mates, or is it the boring guy? It's la 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 la. Come here, come here, come here, come here. There are scientific questions that people want to answer. This is a very well-studied data set from the wood Peewee bird song. This particular data set consists of a song that's a sequence of 3 very well-specified syllables or thongs. These are their spectra. This is an example of the audio signal. And we had 1,327 samples. This is a signal that has an alphabet size of 3. And it's somewhat surprising and very exciting that with these few samples, we already get a fairly complex model. So just like Monique in the previous talk, these birds are not IID. They have structure. They don't just sing random songs. There's very clear evidence of very specific syntactical structure. You can see that the model we get here has a posterior distribution of about 12%, whereas its prior is 4 times 10 to the minus 5. So there's a huge difference between the two. So there's very, very, very strong evidence for this type of structure from the data. And you can play the games that we played before. You can compute the first 5 most likely models. We see that they're all quite similar. And we see that their posterior distributions, there's a clear winner with a posterior probability of 12.6%. Then we have a bunch of models with probability around 2%. The total posterior probability of these top 5 models is just 20%. So we've only explored 20% of the posterior. Let's do some MCMC and see what happens. We ran the MCMC algorithm that I showed a minute ago for 1 million iterations, and it turns out that it visited 300,000 different models. And here's this just indicates that MCMC has converged. These are different realizations of the posterior frequency, the MCMC frequency of the top 3 models compared with their actual posterior probability that, remember, we can compute. And the fact that they converge indicates that the sampler is likely converging. Here's an interesting thing to look at. This is the histogram of the model depth. This is the posterior distribution of the memory length of the data. Although all 4 of our models had memory length 4, you see that the actual posterior distribution is less clear. Yes, memory length 4 is the most likely value, but it's by no means a unique winner. This is, by the way, a way to do principled Markov order estimation without talking about error exponents and things like that we've been talking about asymptotically. In a Bayesian sense, this is the answer to the Markov order estimation question. How much memory is there in the data? This is what I think, this histogram. All right, and then you can do a little bit more. Remember, we have an MCMC algorithm that gives us samples from the posterior on models and parameters. What is a model and a set of parameters? It's just a Markov source. So each one of these has an entropy. So we may want to ask, what's the posterior distribution of the entropy rate of these samples? Or in other words, how do we do Bayesian, truly Bayesian entropy estimation based on empirical data? And this is how you do it. You get your samples from the models and parameters, from the posterior distribution, and for each one of them, you compute the entropy. That's a sample of the entropy under its posterior distribution. This entropy, you can either compute it directly, or for bigger trees, this gets really messy because you have these really ill-conditioned Markov, very large Markov matrices. You have these dimensionality issues. You can just add yet another Monte Carlo step where for each model and parameters, you simulate very quickly, a few thousand data points, and you estimate the entropy of those simulated data points. Whichever way you do it, this is what we get for the bird song. It's very nice and very gratifying that this posterior looks really Gaussian, as it should be. Despite the fact that we don't have a lot of data, it looks like that there's enough data for the type of distribution that may have created this data to give a very well-behaved posterior. And it turns out that that bird song, I wish I had it, we had to switch laptops, so this is not my laptop. I'll play you the bird song later so you can get an idea of what it sounds like. But it turns out there's 0.2 bits per second in their bird song. So, they're not saying an extremely complicated story, but they're not just saying la, 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 la. There is structure there. Okay, so there are 3 more applications I want to briefly talk about if we have time. What time do I have until? Okay, so I have another 10 minutes. Okay, that's 3 minutes for each one. The first thing you can do very, very effectively with the CTW without doing any of this MCMC stuff is prediction. Prediction in a Bayesian setting is done with respect to the posterior predicted distribution. You just want to average everything out and look at the probability of the next symbol given what you've seen so far. Again, Bayesian statisticians will tell you that this is something we can't compute for the usual reasons. They'll just write it out as the average of the likelihood that they can compute with respect to the posterior. This would be the predictive distribution if I knew the model and parameters. I don't, so I average over the posterior distribution. This I can't compute because of that prior predictive likelihood in the denominator, but now we can because of the CTW. So instead of doing all the funky things that they generally do, numerical stuff and model averaging and so on, we just ran the CTW twice, or you can even do something smarter with the CTW that I won't talk about now, and you can compute this posterior predictive distribution exactly. So here are some actual empirical results on 2 data sets. This is the Peewee bird song data, the data set that we just looked at, and this is the bane of our existence over the past 2 years. This is the gene of the spike protein in COVID-19, in the SARS-CoV-2 genome. Here, what we're seeing is the log loss achieved by 4 different methods. The CTW predictor, which is the red thing, and 4 others that are sort of the state of the art. One is Raftery's mixture transition density or mixture transition distribution models, a very recent method on using tensor factorizations by Danson. Another information theoretically inspired method, VMMC, that's more related to resonance context algorithm, a dislike for which by Frans led to the CTW, and another Bayesian method called sparse Markov chains. So this is log loss, which means that small is good. We want a small cumulative log loss, and we can see that these are honest empirical data. We didn't fiddle, we didn't pick and choose. This is what we actually got. This is 50-50 training the model and then predicting. This is 90-10, just because if we did 50-50 here, some of these other methods did outrageously badly, and they needed more training. If we did 50-50 here as well, we'd be winning by a much bigger margin. So the CTW predictor does very well on actual data, and we've done other examples that verify this. Now, it's not just data, there's a lot of theory involved. Here's a very brief description of some of the things that one can prove. One, again, going back to the 93 preprint that never saw the light of day, is that if you follow the ideas in the special case of a proof that they had, you can show that the prior predictive likelihood, the likelihood of the data in this setting that's computed by the CTW, the CTW probability assignment, is uniformly close to the log likelihood of any model with any parameters. And the penalty you pay is the smallest possible. You want this to be as large as possible, right? You'd like this to be maximum likelihood. You can't maximize everybody at the same time, or you won't be able to normalize. So it turns out that the log likelihood is close to the true likelihood, and you just pay this half log n bits per degree of freedom penalty that we know from Rissanen and others via MDL considerations. The predictive distribution converges to the true distribution under very general regularity conditions. With probability 1, the CTW predictive distribution will give you the actual distribution given by the source, which is the best you can do to predict. And in fact, it achieves the best possible log loss of any other method. And for estimation and model selection, these asymptotic results just tell you that things are as they should be. In other words, you have consistency, you identify the right model and the right parameters asymptotically, and the parameter estimates are asymptotically Gaussian. The posterior is Gaussian. Anyway, this is just to show off a little bit, to say that this is not just playing with data and algorithms, there's theory to justify what we're doing. Right, so the last two applications. The first one is Changepoint detection. This will be an outrageously complex hierarchical Bayesian model. If you showed this to most statisticians in this business, they'd say, you know, this is way too much going on here. Here's the too much that's going on. The model class that we'll consider, this is our data, x1 through xn. We assume that there are some change points where the distribution changes. We don't know how many, and we don't know where they are. But let's say they're between 0 and some L max. This is the number of change points L, and we put a prior distribution on them. This is a conditioned Poisson. Given the number of change points, their locations, we put a prior distribution that makes them basically as random as possible. It says that they have the same, the locations have the same distribution as what I would get if, you know, to get 10 change points, I would pick 21 locations at random without replacement, and then for my 10, I would pick every other one, because I don't want to have change points right next to one another. So you pick the even points in 12 plus 1 independent draws without replacement from the collection of all possible locations after you've ordered them. Then after, given the number of change points and given their locations, we are assuming that in each segment, the data has a variable memory Markov distribution given by a model T and parameters theta, each of which has an independent prior as the one that we started with. So we're assuming that here, here, and here, you have an independent collection of models and parameters. The prior on the models is the original prior we put on models, and the prior on parameters is the original prior we put on parameters. You can write out a likelihood, but if you just wrote this down, you'd think this would be hopeless, because unlike the case of the original problem, here we cannot compute this holy grail, this denominator anymore, and just doing MCMC would be hopeless, because at each step you need to choose a number of change points, a location, different models for each segment, and different parameters for each of those models. This is way too much to ask for, but CTW again comes to the rescue. You can integrate out the models and parameters, and you can actually do effective MCMC. Of course, I'm not going to say anything in detail. I'll just show you some results on two very well-studied data sets. This is the well-known circular DNA genome of virus SV40. There's a well-known change point, And this is the posterior distribution on the location of that change point that we get. So this is very, very well and very clearly identified. This is just a blow up of that circle there. Same thing with another well-studied genome of a bacterium, the enterophage lambda bacterium. This is the structure, this is from Wikipedia. This is what the biologists tell us, that there are two biologically determined change points. This is the MCMC histogram of the number of change points, and we actually do find them quite convincingly. This is the MCMC histogram of the locations. One is around 22,600, this one, and the other one is around 27,800. This is this one. All right, so finally, the last thing I want to describe is how you can go from the discrete to the continuous, how you can deal with real-valued time series. And the idea is you quantize and you mix. So the main thing I want to describe, I'll show some pictures just to convince you that we do get reasonable results, but the main thing I want to describe is the class of models. So how would you use this very discrete construction, this very discrete context, concept, I'm sorry. Bless you. Have you been to China recently? No? But I really want to give the idea here. And the idea is very general. Start with any class of your favorite continuous time series models. You just say your ARMA models, or moving averages, or set-R models, whatever have you. So now take your data. Find a meaningful quantization of your data. Let's say it's financial data that I'll show, for example, in a moment. You can say I quantize to 3 values. When it's a stock price, I can say it's 1, 0, or -1, depending on whether it's gone up, down, or stayed the same compared to the previous day. So first quantize your data. Now create a context tree model for the quantized data. And now put a continuous model at the leaf of that discrete tree. What does that mean? In practice, it would mean the following. Take my data. To describe the model, I'll just describe the predictive distribution. Let's say I have my data. I want to predict tomorrow's value. How would I do it if I knew a model from this class? I would discretize the last, say, 10 samples. I would look at that context, that discrete context, see where it takes me along a context tree, go to the leaf of that context tree, and read off a different AR model given that discrete context. So now I'm doing, what we're doing is creating a very broad mixture of set-R or ARIMA or ARMA models. You just do a very broad mixture class of time series, continuous time series models using what statisticians like to call state space partitions. So I just said in words what these steps say here. What's really beautiful and really exciting is that all the algorithmic tools and all the theory generalizes to this case. And we played with some data. This is one example. I'll show, this is the unemployment data per quarter in the US from 1948 until now. We look at the differences between different quarters, and we quantize 2 values, as economists do. If unemployment stays the same or goes down, it's a stable economy. If it's going up, we have an economic contraction. This is the model that it turns out the data supports. Just 282 observations already give you structure, and this structure can be used to produce a model that does better at prediction than the state of the art. And this, if anything, is a super well-studied model for problem and data set for which very specific model classes have been employed. So this is the most recent, most exciting, at least for me, thing we've been doing. That's all I wanted to say. Just in closing, I wanted to mention that information theory over the past at least 30 or 40 years has been acting as a a guiding lighthouse, as an important intellectual guideline in our understanding of the foundation of statistical ideas. So mostly we use information theoretic ideas in statistics in connection to foundational questions when we want general guidance in interpreting and understanding what's going on. Not so much in actually producing methodologies that are used in practice. And I think the hope does remain that information theory will in fact have a major impact in providing such methodological tools that will be taking over and be used in mainstream statistical practice. And I think the CTW, to a very significant extent due to France's efforts, may play a major role in realizing this hope. So I'll stop here.